is to talk about the backpropagation in logistic regression and how it works. You can represent even the logistic regression with neural network with one input layer, output layer, a very simple network. So we will see how backpropagation can help us update the logistic regression and make it more fitting to our data. Backpropagation is one of the most important algorithms in deep learning, especially in neural networks. So let's look at the logistic regression, which help us quantify our data for a classification if what is the probability for something to happen between 0 and 1. And we want to adjust our system so that it gets another example and can tell us what is the probability to get a 0, 1, or any number between them for the probability. And so as you can understand, we need to train our data, our model with data, and we are doing it using the backpropagation algorithm. We are updating our weights, and this is how we adjust the logistic regression. So we start with this is the definition. We take the x, which are the values, and b, which is the bias, and weights, which is the weights in our system that will be adjusted. If you're looking at neural network, maybe I need to show you this. You will see here the weights. I'll show you the weights. Here it is, for example. So you can see that we need to adjust the weights that are on the edges until we get to the final result. We want to adjust this weight. Those are the x, which are the input values. Input layer, all those x is one example from our data. The w's we need to learn them, we need to update them. We will start them with the random numbers. Bias also we can learn it. We started with a random number. Then we will do the function, which is sigmoid function in the case of logistic regression, and then we sum that, and then we're moving it throughout the logistic regression, and then we'll get a prediction, and we'll adjust it based on the known prediction that should be on the sample and what we got from the model. And the difference will create us the loss function, which will be the cross entropy, because the cross entropy is the loss function that can be used for this classification type, this problem type of 0 to 1 of probability. So we are calculating all of this, which exactly what we get from here. We are multiplying the x by the y's, summing them up, and also taking the b and summing them up, and then doing the activation function, which is the sigmoid function here. So this is the summing up. We will call that z, and then we are applying the sigmoid function. We will call that y hat. We're applying the sigmoid function on the z, which is the summing, and we're getting the sigmoid function, and here is the minus z. You can apply this one here. And we will use the loss function to evaluate the result we got from the model using the cross entropy. Cross entropy loss, log loss, sometimes it is called, you can see here y, this is the true label, times log of y hat, which is what we got from the model, plus 1 minus y. Remember that y can be 0 or 1, and the y hat can be somewhere between 0 and 1 because it represents probability. So 1 minus y, again, y is the true label of the example, times log y minus y hat. Again, this is the model evaluation, the probability it gives for the specific example we are doing now. Okay, so this is the loss function, and we need from this loss, from the error we get, to learn the new weights, how to adjust the new weights, how to adjust the weights, how to change them such that the network will be more fitting to the data. Here there is a risk for overfitting in the neural network in general, but we are fitting the model to the data. We are adjusting the weights. We adjust the bias using the loss function, to get better results, what we are doing that we are taking the derivative with respect to each weight and taking the negative direction of the derivative. It will give us reduction in the loss function, which is the gradient descent, what we are doing. And again, we will take the derivative also of the bias, and again, change and update the bias in the negative direction of its derivative, again, to make the loss function lower, to make the model more fit to our data, less error. So we are starting the back pass. We need to take the derivative with respect to each w, with respect to b, and using respectively of this to update the weights. So we are taking the loss function with respect to y, then to y hat, then we'll take the derivative of y hat with respect to z, and then we'll take it with respect to wi, and we can use it to update wi. We will also take the derivative of the loss function L with respect to the bias B, and we will use it to update the bias. So we are using here the chain rule, because here, as you can see, I can't take directly the derivative of this with respect to W because Wi is not here. Wi is inside the y hat, inside the z, here is W. So I need to do a chain rule in derivatives. So I'll take the derivative of L with respect to y hat, derivative of y hat with respect to z, and derivative of z with respect to wi. And then I will get the derivative of L with respect to wi. So it's the chain rule. Can you show me the total chain rule you used? And he will show me how to use the chain rule. You can see, here it is. You can see how it takes the chain rule. It takes the derivative of L with respect to y hat. If you take the derivative of this one with respect to y hat, you will get this value. This is the derivative. And now we'll take the derivative of y hat with respect to z. As you can see, y hat is depends on z, so take the derivative of y hat with respect to z, you will get this one. This is the derivative of the sigmoid function. You can remember this value. Derivative of the sigmoid function look like, you see it's very nice. Here, the derivative of a sigmoid function is just this one. So you can remember this. So just take the derivative of the sigmoid function with the sigmoid function times 1 minus the sigmoid function of z. So this is exactly what we did here. This is the sigmoid function times the 1 minus the sigmoid function of z. And z is just what? Very easy. Let's go back. Okay. So we took the sigmoid function, the derivative of y hat with respect to sigmoid function after we took the derivative of L with respect to y hat. And then we want to take the derivative of L with respect to W. Here somewhere. Okay. Okay, so the derivative of L with respect to Z is the derivative of L with respect to y hat times derivative of y hat with respect to Z. We're still not in the derivative of L with respect to Wi, which we want, but applying the values we calculated. So here it is here, this is here, and that one is here, here it is. So we can use it. And this is the result from this. And now, we've already done that. So calculating this, we're getting that one. Now we just remain with taking the derivative of z with respect to wi. Now remember, this is the value for z. We represented there using matrix representation. Here is the simpler representation. This is z is the sum. Now taking the derivative of z with respect to wi will give you just the xi, which would correspond to the wi. Now you can take what we want, the derivative of the loss function with respect to wi we want, which is the derivative of L with respect to z times the derivative of z with respect to wi. So totally what is written here is derivative of L with respect to y hat times derivative of y hat with respect to z times derivative of z with respect to wi. You see here the chain rule. Okay, so we can apply this one. We also already calculated this. Here it is. Here it is. Times derivative of this with respect to the xi, which we saw is just the x with respect to wi, which is just the corresponding xi. So this is the total chain rule. And we can also take the derivative of z with respect to b, which is the bias, which will thus be 1, right? So the derivative of loss function L with respect to b will be the derivative of L with respect to z times the derivative of z with respect to b, which will be just this one times 1, which is this one. Okay, so you can see the summary here. Starting with L with respect to y hat with respect to z, and from this one times this one, we get the L times respect to z, and to get L with respect to wi, we take this one and multiplying by the derivative of z with respect to wi, which is here. And we can also take this and multiply that one by the derivative of z with respect to b, which is 1, and then we get what we want. The derivative of the loss function with respect to wi, derivative of L with respect to b. Okay, so this was the chain rule. When you go back, you can see all of this here. Here it is. Here we did just the same. We take the loss function with respect to all what we said. We apply the chain rule to get the L with respect to Z. Then we take the L with respect to Z times Z with respect to Wi to get the full chain rule for L with respect to Wi. Did the same for L with respect to B and got the derivative we wanted. Now we want to update the weights and the bias. We will use learning rate because it's just adjusting the rate of which we learn. We don't want to learn too fast because we can overshoot if we are learning too fast. So we are using the learning rate, how it is called. Let's call it n because it's similar, and we can adjust it. Usually they take something like 0 point something, a small number, not a very large number, to make the learning rate a little bit slower. There are many methods. Sometimes we start with high learning rate and then reduce the learning rate because when we are getting to the optimization point, to the extreme, we want to learn slowly so we are not overshooting the extreme point. We want to get to a minimum as much as we can. So this is how we update the weights. We're taking the weight and we reduce because we want to go in the negative direction of the gradient. Remember, the gradient also always head to the direction in which the derivative gets bigger, increase, but we want to decrease the loss function. We are taking the derivative of the loss function, we want to decrease it. Therefore, we want to go in the negative direction, in the opposite direction of the gradient, which will increase, which will moving in the negative direction, the opposite direction of the gradient will decrease the value of the function and it will get us to a minimum point. So we're taking the wi and reduce n times the derivative of the loss function with respect to this weight. And we are applying this and we are getting this one. For the bias, we are doing the same, moving in the opposite direction, but now the derivative of the loss function with respect to b, and this is the formula. Now let's take an example, a very simple example with only one example, and this example has only x1, not x2, not x3. Very simple example. You can see here the feature, the true label which should be 1, and we see what the model will say. The initial weights randomly take W to be 0.5, initial bias randomly to be 0.1, and learning rate, you see the learning rate is quite small. Now the z of us is this one, and we apply the numbers, we get this. What the model says, we are applying sigmoid function on the summation and get this value, which represents probability, which says that the probability now, as the model is now, of x, this one, to be 1, which is the true level in that case, is 0.7, namely 70%. Now the true level should be 1, so we have a little error. So this calculates the error, as you can see here, and you can see that we have an error applying the values, and now we want to update the weights and the bias using the backpropagation algorithm by using the derivatives, using the chain rule, and then gradient descent to update the weights and the bias. So we are taking the derivative of L with respect to y hat, and then L with respect to z, and then L with respect to w, and then L with respect to b. We're using this and this to update the weights and the bias respectively. So we know the formula for this. We don't really need to calculate this. We can just use the formula we got last time instead of calculating again all of this. And we can use the formula we got there. If you remember, this was the formula for the weights, this was the formula for the biases as a derivative, and we can apply the values. Y hat, we calculated this here, and y, we know this is the true label, which in this case is 1. It could also be 0, but in this case the true label is 1 because we know that the true label is 1 because this is our data. So we use this, apply this here, and multiplying by our x, which is this one. This is our feature. And we get the value for the derivative of L with respect to W. We are doing the same for L with respect to B, but now if you remember, this is the formula. Here is not x, it's just multiplying by 1. And this is the formula. We're applying the values, y hat, which is the model result, y, which is the true result, which is the true labeling, and this is the result. Now we want to update the weight and the bias. We're taking the weight and subtracting n, which is the linear rate, times the derivative of the loss function with respect to this w. We have now only one w because it's a very simple example, but you could also have many weights, many w's. So here we apply this and get the result, which is our new w minus linear rate times the derivative of L with respect to w. This is the new weight. You can see how we apply this and we update the weight. And we also update the bias in this, and updating the bias give us this one. So here we update, we have now a better model. We can again run data on the new model with the new bias, with the new weights, and see what the result, get the loss function, again, calculate the backpropagation and updating the weights and the bias to get a better fitting model. Now it was a very simple example with only one weight and only one data sample because I wanted it to be simple, but I wish that you understood how taking the backpropagation, in this case using with the logistic regression, with the cross entropy loss functions. There are many different loss functions for the different scenarios with different functions, but in the logistic regression you can use cross entropy loss function. So I wish you saw how this idea is done. These are the x, those are the x's, those are the weights, summing them up with the bias, making the function activation function. In the case of logistic regression, this is the sigmoid function, getting a prediction, calculate the loss, calculating the derivative with respect to w's, with respect to b, using the chain rule, and then updating the weights and the bias to get a better model. And then we can use another example, again, to calculate the sum, calculate the activation function, calculate the prediction, and again, calculating the loss, taking the derivatives with respect to each w and bias, and updating and getting a new model, a better model, until it fits better and better to our data. Remember that we can get to a local minimum and not a global minimum. This is a problem, but okay. And we have a very important risk of getting overfit to our data. This is another thing. And that's it. This was about logistic regression and and how we can use to represent it as a neural network and use the backpropagation to update it and make it better. Thank you very much. If the logistic regression is used to evaluate for each sample what is the probability between 0 and 1 to something, that's it. If there are any correction or mistake, please correct me, and that's it. Thanks ChatGPT for the calculation and then everything, and thanks for the images.